Okay, thanks a lot, everyone, for being here. So, for those who have seen the announcement, there was a title announced. In fact, today I'm going to talk about something different. The talk planned initially will not take place today, but possibly in the near future. But I still hope this will be of pleasure to everyone here. So what I'm going to talk about is a synthetic approach to infinity one category theory, and this has some tie-ins to several. To several Topos colloquium talks given by several people, notably one kind of recent one by Riehl Verity, who talked, who talked about one such approach, but in fact mentioned another one, and I'm going to talk about this other one today, which was not really covered in Dom's talk. So I guess the main topic of Dom's was infinity cosmos theory, but in fact this other approach that I'm going to talk about today is some approach based on type theory, namely simplicial homotopy type theory. Okay, so what is the story here? So, right, so I guess we're all familiar to quite a notable extent with ordinary category theory, one category theory, or some kind of higher dimensional category theory, and there okay, so when we define what a one category is, I think we all have like a common picture in mind. So it's some structure where we have a notion of object and arrows, and the definition of a one category, it can be presented in different ways, but essentially it's not, you have to pay a little bit of attention, but it's sort of clear what they should be. Now, in the business of weak higher dimensional category theory, it's sort of not so clear. So the idea of like a higher dimensional category is that we can have not just arrows, but we can have some higher dimensional things. So we can have two cells between one arrows, and so on, all the way up. And specifically, in the case of infinity one categories, we might have these higher dimensional cells in arbitrary dimensions, but in fact everything above one will be invertible. So it will be trivial in a specific sense, but it's still a lot of data that we have to keep track of. And so the jump from one to infinity one category theory can then be seen as sort of, instead of a set of objects and sets of morphisms, instead of taking those, we transition to take a whole space worth of morphisms. So these infinity one categories will be something which has some sort of topological or homotopical structure, and there exist many different models of what a one category could be. It requires a lot of one-categorical setup to say what those should be. So some models are based on pre-sheaves on certain categories, but that's not the only way to go. But in any case, it still takes somehow some amount of one-category theory to be developed. So yeah, there exist many models, and it's kind of a lot of work to set up in set theoretic foundations. Okay, so, and one other thing is that, okay, when working in set theoretic foundations, not only is it actually, I mean, it's kind of easy to say what the intuition here should be, but it's not that easy to make it precise. But also, when working in set theoretic foundations, we're dealing with these homotopical structures, and every time we want to actually do something to our categories, look at the opposite category or something like that, perform some categorical constructions, we have to make sure that the right notion of equivalence gets respected. And that's a lot of manual work to check in set theoretic foundations. So what about homotopical foundations instead? So what do we mean by homotopic of foundations? Of course, in set theoretic foundations, the basic notions are just sets, which are some collections of elements with no additional structure sort of given a priori. But the idea in homotopic of foundations should be that the basic objects would be something the basic objects would have some kind of topological or homotopical meaning. And so one kind of popular system here is homotopy type theory, where the basic objects are not given as, they're not sets, but they're thought of as homotopy types, which are topological spaces considered up to homotopy. So yeah, I mean, it's a big topic. There can be said a lot about this, but for today, let's just look at some sort of basic ideas to see, yeah, how can we get from these homotopy types to higher categories. So one application here is that since these basic objects are now something like topological spaces, we can do we can do a lot of synthetic homotopy theory. So this is what is enabled in this foundational system. And in fact, changing the foundations here really has practical purposes in many ways. So there exist proof-assistant implementations where we can mechanically check that our proofs are correct. So we can do homotopy theoretic, we can write up some proof of some homotopy theoretic computation, and then we can verify it in a computer. But also the models of this theory, they are given by a large class of a notion of abstract homotopy theory as given by infinity toposes. So what exactly those are is not so important, but they include the sort of standard notion of topological spaces, but also other more non-standard notions that are relevant in modern day homotopy theory. And the point of this is one can do a lot of the sort of classical theory, interpret them in many contexts, and just get a whole range of theories out of this. And yeah, of course, when we're changing our foundations, we want to know what exactly are we changing it into. So the basic notions in type theory are these things called types. So that's just something, some sort of object, and the object also has elements called terms. So we can have terms little x, or let's say little a in big A, which are like elements in set theory, where instead of the element symbol, we write the colon. I mean, okay, so far so good. That doesn't look so different. But the point is that the way that the types are constructed and the inhabitants of the types are constructed, that's really, that works really differently in type theory than in set theory. So yeah, I don't want to go much into detail about the underlying logic behind this. Let's look at the more, yeah, let's look at the exciting stuff that actually makes, I mean, that actually reflects this homotopical picture. So we can perform in type theory a lot of constructions on the types. So for instance, given any two types A, B, we can form the Cartesian product type A and B, and whenever we have elements like this, we get inhabitants of the product type by these pairs. We can also form, we might be able to form coproduct types and so on, all sorts of things. But something that is important in homotopy type theory is the idea of identity type. So the way that identity works in set theory is, well, I guess I guess there's one naive way. Which we could call just equality, and then there is the not so naive way, which we could call it identification. And so set theoretic equality, well, that's, I mean, that's basically, I mean, we can model it as a relation, the diagonal on a set, and it will just equate two elements which we can prove to be equal, to be exactly equal to each other. But then there is this other more interesting notion of identification, or maybe in more familiar terms, isomorphism. And this is some sort of non-trivial thing where we say two structures are isomorphic in a category or something like that. But of course, this is some notion that is really built out of this very strict notion of equality here. And in type theory, this kind of more refined notion is really built into the theory. So in type theory, we have this notion of, so we have two types, we have two kinds of ways of being equal. So we have judgmental equality and propositional equality. And judgmental equality is, it's it just, I mean, we can write it in this way here. So indicating two terms being equal, two terms of the same type being equal by this sort of congruent symbol. And these equalities are given to us by the rules that we introduce on these type formers that we have in the theory. But they are sort of, I mean, often terms that are regarded as equal, they are not equal in this judgmental sense. This is some sort of logical, maybe artifact. And it's actually, I mean, it's actually good to have relatively few judgmental equalities in type theory like that, because it retains some good computational property when we actually care about implementing this in proof assistant. So for example, if you were to define a type of natural numbers and addition there, I mean, even there, the sort of very basic identities that you use to define the success, or that you impose on the successor function or something like that, already those you would not be, you would like not to have them all hold up to judgmental equality. So instead, what you use is this thing called propositional equality, and this is something along the following lines. So whenever we have a type A and inhabitants A and B, then we can form, we can ask for A and B to be equal, but this is not going to be, in general, this is not going to be a proposition. So in general, we actually look at all the types of sort of proofs or evidence that A and B are equal, and this gives us a new type. And okay, so now I've sort of given the signature on when we can form this kind of type. So whenever we have two sort of points in a type, we can ask, well, yeah, we can ask, okay, are they equal? So we can always form this, and I mean, sometimes that may be the case, and sometimes there might be no inhabitant there. So there will always be an inhabitant of the type A is equal to A via the reflexivity path. Okay, this is some sort of information that is given when introducing this type in the system. And at first, this may look also sort of, a bit. It seems like it doesn't tell much, but the point is that just like we can understand the natural numbers as being inductively generated by the zero element and the successor function, we can understand this identity type being inductively generated by this reflexivity term. And that's a very crucial and very powerful principle, which I won't state here, but let's take note that there is a thing like this. So induction principle for the identity type generated by reflexivity, and this sort of induces a lot of more structure. So we want our equality to really behave like equality. So we already have evidence that equality in this sense is reflective, but it'll also be symmetric, meaning we're going to get functions. I mean, for every pair of elements, we're going to get functions like this. And so, I mean, this is sort of, I'm separating this. So this is given. And from the inductive generation, we can prove, for instance, these kind of symmetry and transitivity laws. So I'm not writing down the transitivity, what it actually means, but you can take a guess, and it'll be correct. Yeah, I mean, yeah, for those who have seen this before, I mean, the precise formulation here would be path induction, which is sort of exactly this induction principle here. But okay, I don't want to go into this. So the point is that, coming back to the topological picture, okay, we now have this sort of refined notion of equality, which we also consider as a kind of path by this here. I mean, symmetry means, okay, if we have a path from A to B, then we also, I mean, we can like travel it, you know, in reverse. And of course, we can connect paths like this somehow. So we could imagine our types to be something. We could imagine our types to be interpreted as some kind of space that homotopy theorists care about, because in homotopy theory we do care about things like paths and loops and that kind of stuff. And that's actually true in a very vast sense. So yeah, in these models, the types are really going to be something like this. But in the internal language, we don't see the models as such. But even in the internal language, we can kind of see that these types have the structure of a space, and we can do homotopy theory with them, because every type gives rise to a sort of family of identity types, A to B, A equals B. But this can be iterated. So whenever we have two, I mean, let's say we have A here and B here, and we have two paths like this, we can look at like higher dimensional paths between them somehow. So I don't know, something like this here, some phi, some 2 cell here, and so forth. So we can iterate this. And this shows that types, even internally, have the structure of a higher dimensional groupoid. So we can say something like types are infinity groupoids. And the groupoid, I mean, yeah, the groupoid laws really come from this kind of these kind of functions witnessing that we're really dealing with the kind of equivalence relation. And it turns out that also, I mean, it's been known to homotopy theorists that in many contexts, notions of infinity groupoids really homotopically correspond to spaces, or I guess, yeah, homotopy types, if you prefer this term.
Can I ask something?
Yes, please.
Okay.
Yes.
So like this is like the Grothendieck homotopy.
Exactly.
Hypothesis.
Yeah.
So, okay, so I'm not that familiar, but I was under the impression, I guess, that like in certain models, that like in like the infinity cosmos like sense of like certain models, like you can prove that like that's like an actual theorem, but isn't it just like originally something that Grothendieck was like, this is how it should be, but it's not like, you know, so I mean, are you saying like are you saying in this context it's just like a similar thing, it kind of feels like that, or is there an actual theorem that's like in this homotopy type theory sense, you can like actually prove that like a correct notion of space is?
Right. So so there is a standard semantics or standard model where you can really make sense of this for this particular model. And I mean, this classic sort of equivalence of homotopy theories. So you have some kind of specific, so I mean the name of the model would be Kahn complexes, and that those correspond to spaces. That's a rather classical result. So I mean it was known before. I mean before type theory really was became you know such a thing. But yeah, but the insight about 15 years ago and counting was how to connect. I mean how to interpret, or even how to. I mean if it were possible, and if so, then how it would be possible to interpret type theory or homotopy type theory here, right? So that's kind of the new thing. Yeah. Does it answer the question?
Yeah.
Yeah. Okay. So now, okay. Now what do we have? We have some kind of setup where, we can do homotopy theory synthetically. So we haven't really seen it, but we can kind of believe it with these kinds of considerations. But now when it comes to, and we also took note that, well, our spaces are kind of like infinity groupoids. But what about higher categories now? So infinity one. So when we talk about infinity one categories, we should have a sense of direction, which we don't have for homotopy types, because we can always, because they're infinity groupoids, we can always invert the paths, but that shouldn't be the case for arbitrary given infinity one categories. And so how do we deal with that? I mean, yeah, how could we try to devise a similar language where we can deal with these kinds of things? So there might be several answers to this, but one approach is due to Riehl Shulman, and the idea is the following, namely extend hot by some more stuff, namely some specific shapes that sort of captured this sense of direction. So what kind of shapes do we need? So we want to talk about arrows. So yeah, it would be good to have an arrow like this. And okay, we also would like a point. And then, of course, in a category, we don't want to just have arrows, but we want to have composites of arrows. So one way of modeling composites would be via a triangle or a two-simplex, like this. And of course, we want to be able to look at longer and longer paths. So yeah, we might ask for also this three-simplex here somehow to be captured, and so on. So in this kind of extended type theory, what we do is we look at all these kinds of simplices. So I can call them delta 0 for the point, delta 1 for the arrow, delta 2, and delta 3, and so on. And these are, so yeah, these are used, or these will be used later to say what exactly a synthetic infinity one category is. So one thing that we take in addition to our homotopy type theory is this layer, is an additional layer of simplicial shapes. Of course, it's not, I mean, okay, these pictures look nice, but it's not so clear how to actually define these simplices like out of nothing. So, I mean, the way it works is we're actually going to start with the kind of, we're actually going to start with something cubical. So we're going to start with an interval, with a directed interval, which looks just like the one simplex. But then we're going to consider powers of this. So, of course, we also have the point again. Take the second power and so on. And this gives us, I mean, we can imagine this being embedded in some discrete coordinate system. And then these kinds of shapes, they will all live embedded inside these kinds of cubes. So, I mean, here, these are sort of the same somehow. And then when it comes to the higher simplices, they will all live in a higher cube. And okay, that's, and I mean, okay, we have to have like a means of defining these certain subsets of these cubes, but that's something that we can do just through conditions on the coordinates, and that's so you add some sort of logic for these shapes into the layer, into this layer here. And the point is because we really want to have the sort of free one categories of these shapes, and not something per se higher dimensional. The equality in these, in this, I mean, in this kind of like lower dimension, I mean, in this kind of more basic shape theory, that should be extensional or judgmental, so or strict. So equality is strict in this part of the type theory. Yeah, so we really want like a literal arrow. I mean, later on we will want to look at maps from the arrow into a type, starting at some A and going to some B, and we really want this to be a literal arrow from A to B and not just an arrow from some A prime to some B prime, where we have a path from A to A prime and a path from B to B prime. So that's not what we want. We want something strict here. And so it kind of makes sense that these shapes are defined in a strict way. Okay. Now when it comes to relating these shapes and types in a useful way, what should we be able to do? So I said the infinity one categories are supposed to have the sense of direction. So we want to be able to form a type of homomorphisms from A to B instead of just paths between A and B. And so these paths should be special cases of the homomorphisms. They should exactly be the isomorphisms in the right sense. And I mean, to sort of show this connection more clearly, I'm going to be writing these homomorphism types with the arrow here. And how exactly, I mean, how could we define or introduce such a type? So there's one more gadget which we add in this theory, and it's called the extension types, which are defined as follows. So suppose we have a type like this, and suppose we have some shape inclusion psi into phi like this, and we are given some term or some element which is defined on the smaller shape. Then we want to look at the collection, or more precisely the type of all these extensions. So I'm writing it, I'm introducing a new type for this, which I'm writing in the following way. So it's going to be all functions from phi to A that on psi, that restricted on psi give us A. And well, okay, that's not a definition, but it's kind of the the image that you should have in mind. So I mean, the whole thing is not a definition, but that's what the result is going to be. But now we have to be a little bit careful, because what does extension actually mean here now? And the point is, so the inhabitants of this extension type, they're going to be all the b's from phi to a, restricted on psi, give a, such that this restriction holds judgmentally. So we could write b restricted to psi is judgmentally equal to a. So this is exactly the difference between like having arrows strictly from a to b versus having arrows from some other point, you know, arrows up to sort of homotopies of the endpoints, if you like. So it's not because, okay, I didn't say this in the beginning, but it's kind of crucial, because one could think that in general, I mean, it's always the case that from here we can produce an inhabitant of an identity type. So given a strict equality, we can always reflect it as a path in this sense, but not the other way around. So that's in general not possible.
How does the extension types relate to pi types?
Say again?
To pi types?
You're asking if like how the extension types are related to pi?
Type of like
Yes.
E over A.
Absolutely, absolutely. It's absolutely what they are. So, but there is this little twist. There is this little twist how to reflect this appropriately in our syntax. But in the semantics, that's exactly the right picture. So we could look, I mean, okay, so yeah, I'm not using the term pi type, I'm just saying function type. So it's true that there exists a dependent form from this as well, which would be the step from the ordinary function type to the dependent pi type. But yeah, let's look at exactly the categorical semantics of this. So we start off with the shape inclusion psi to phi, which means we can take the exponential, we can exponentiate a by this inclusion, get a map like this. Then the term a here will be a global element of this, and the extension type is exactly this pullback here. Yeah, so in the semantics there's sort of a lot, I mean, yeah, I mean that's basically what you should think of here. But the point is that the point is now the following. So I haven't discussed how it works, but these categorical constructions we could, I mean, there is a way to say internally in the type theory what the pullback is, but only up to propositional equality. So we could try to define, I mean, try to define the hom type. I mean, okay. Before I say this, let's actually say how the hom type arises here. So, given these extension types, the hom type, yeah, maybe someone wants to do it. Yeah. So, what should be the shape that we're looking at? The basic shape. It should be an arrow, right? It should be a directed arrow. So we have these shapes, the simplicial shapes, and some subshapes of those. And so it should be somehow derived from the type of all functions from the free arrow into A. But then we have to impose the side condition, and that says that on the boundary, which is just 2 points, right? On the boundary, it's the co-pair A and B. And the crucial thing here is now that because of this general pattern of what the inhabitants are, the inhabitants of this hom type will be will be Fs like this, satisfying this side condition, which says that F0 is judgmentally equal to A, and F1 is judgmentally equal to B. And I mean, if one knows a little bit of type theory, one could try to define the homotype more natively within the language of type theory, and then it could look like some kind of I don't want to say subtype, but it's some kind of, yeah, it would be imposing conditions somehow. So
like a sigma type.
Exactly. So we could try and say hom AB is the sigma type of all f's from delta 1 to B. But what do we put here now? What kind of conditions? So we can only write the identity type. We can only use the identity type on A. And these in general, these in general won't be propositions. So it will be, I mean, yeah, these won't, I mean, this will give us exactly this kind of thing, which we have here. Because in general, we can't go from a propositional, propositional equality like this to a strict judgmental equality. And what this means, I mean, the inhabitants of this type, they are not F with this additional information, but they're F and then some P and some Q of this form, like A prime, F to B prime, where here we have P and here we have Q, and here we have B. And so it would be way more, like it's way more data, and it's not the actual thing that we want. It would be very unwieldy to work with these kinds of things. So that's not, that's not the, that's kind of inconvenient. And so that's why we have to go through the lengths of introducing this new kind of type former, but it's exactly introduced in the way that you would introduce function types. I mean, think of lambda calculus, for instance, or the dependent version with proper pi types. The word works exactly the same, only that you add these judgmental equalities to your sort of premises of certain rules, and the computation rule, and of course they will also appear in the computation rules as well. So the point is, externally we can do strict categorical pullbacks, but internally it will be something weaker. It will be something like this. Because here, I mean, here we can't put, I mean, we cannot put this, we can't put judgmental equalities here, because we have to put types here. And the types are non-extensional. The equality types are non-extensional in general. Does this answer the question?
So this inconvenient thing is what you use, or this inconvenient thing is not what you use?
This here? So no, that's not what we want to use. Yeah, so we can.
You want actually equal?
Exactly. So I want this here. I want this here. Okay, and yeah, how can we now say what is actually a synthetic infinity category? So in the picture now, our types are, I mean, they have to be in the model something more general than homotopy types if we want to really do something synthetic, because infinity categories are more general than infinity groupoids. So we can imagine, I mean, our types are now going to be something which we could call simplicial types in the model, and then the homotopy types would be some subclass of this, but let's not delve into this. So our types are still going to be something like a generalized space, but in the sort of next dimension. And this makes it possible to carve out the ones that are actually synthetic infinity one categories.
Certain types are called infinity one categories.
That's right. Yeah, and that's what I'm gonna do now. So we start with the type A, and then we say it's a. Okay. First of all, what do we actually want to define? So we want to define composition, right? So in composition, we can imagine as saying that, okay, whenever I have a pair of arrows like this, where a pair of composable arrows, that should be somehow, the sort of space or type of all of those should be the same as the space of filled triangles. So here, okay, I drew those shapes right over here, but actually the full shape is of course the one where the interior is also included, and similarly the other times as well. So that's what composition is. And the way to define this is by a predicate on A, where we say, okay, a space has composition if, let's look at the, so this here is a kind of shape which sometimes called lambda 1, 2, and this is delta 2. And we have an inclusion of lambda 1, 2 inside delta 2. I am calling this iota. And then A has composition if the map iota is an equivalence. So I haven't said what an equivalence is, but it basically means, there is a way to define, what being an equivalence means for a map inside homotopy type theory. Yes?
So we're thinking about categories here, and we can think about, okay, these are infinity one categories. Well, okay, if we just think about it lower level, they're categories enriched in groupoids.
Yes, that's
very low level.
No, great, yeah.
And in the groupoid case, if your groupoid is not set, if you have a groupoid, if you have a non-trivial groupoid, then I feel like those two types that you have up on the board there, the type of doubles and the type of doubles with an identification, are not going to be equal, because they're not going to be an equivalent, because you have there are like multiple identifications of a morphism with itself, so therefore multiple identifications of like a composite of two morphisms with itself that are not equal.
Okay, so what is your assumption? Like, what is your basic? So you said that's true under some condition. What is the condition?
That the Hom groupoid is not a set.
Ah, okay, right, yes. So, okay, so the Homs here, a priori, they will also be types. They will live on the same level as all the other types. But it turns out if a type has composition, the Homs are still not sets, meaning that they strictly have they only have trivial paths or identification. But here, the types will be, they won't be sets or groupoids, but they will be infinity groupoids again, which is what an infinity one category is. It's like a category, but enriched in infinity groupoids.
Okay. Okay, forget all that infinity nonsense. Like, even if we're just talking about regular old one groupoids, that is, there's going to be I believe that there is going to be a map from that horn to the two simplex that assigns each thing to a filler, and moreover, it assigns each thing to like a canonical filler. But I feel like there's going to be, oh, are you saying that? Yeah, no, I feel like there are multiple fillers that could be non-isomorphic.
Ah, okay, I see. Well, okay, so the point is, they're all going to be identified. I mean, here that's exactly what what this condition says. So it sort of says whenever I have, whenever I'm now in a type A, and the condition here says, okay, given any pair F and G like this, then the type of all of the following data, namely all maps H and all the two cells filling this sigma, so the type of all those guys here, that's going to be homotopy equivalent to a point. So since we're in it, so what does this mean? So since we are, so we're looking at not the set of these guys, but we're looking at the type of these guys, and
and why is that a point?
Well, in general it's not, but for infinity, for certain types it will be, and the property of satisfying this will exactly be the property of having a notion of composition.
Oh, is it like, so yeah, when you're writing like A to the iota, it's like there's an induced map from iota, like that is induced on A by iota, which is like a map between the space of all of the unfilled horns and the space of all of the filled horns.
Exactly.
Right? And so then you're saying like these two types should be like, so you're thinking of like these two shapes that represent those unfilled horns or filled horns inside of A. Those should be like homotopy equivalent, right? That's like what it means to have composition. So if you have two unfilled horns that are homotopy equivalent, then their corresponding filled horns should also be equivalent.
Okay, I wasn't able to parse, I think the last thing that you said, but so you were referring to this map here, right?
Oh.
Yeah, that's like the induced map here. So that would restrict a given two simplex to the 2-1 horn. And the point, the point of this being a homotopy equivalence is if you spell out what it means. We're doing this very intuitively now, but if you actually spell it out in the type theory, it will tell you exactly this.
Yeah, so I guess maybe I was saying it like the opposite direction because I forgot about the change in the direction. But it's like if two filled horns are homotopic to each other, like then they're corresponding like unfilled horns. If you forget about the H, then those should also like be equivalent.
Yes, that's true, and I think I think I understand better now. And I think this is let's see. I think this is even more. I think this is a more general principle. If I got correctly your question, I think this is a more general principle somehow because because you have. That's a type. That's a type. So you have identity types there, and it's sort of it's like, it actually touches another principle of homotopy type theory, but yeah, namely that every map is continuous in the sense that if you have, generically, if you have x equal to y, so you have a map f from A to B, then any map f is going to preserve the paths in the sense that you get a map like this. And I think what you said is would be an instance of this where you use this.
Yeah, I guess maybe. Okay, so it's maybe something like if you had two different candidates for filling in the FG form, right? Then like two different possible compositions. If the restriction is actually a homotopy, or if the restriction is an equivalence, then that means that, well, they both restrict to the unfilled form FG, but that is like equivalent to itself, right? So like if the restriction is a homotopy equivalence, like those things are going to the same point in the codomain, so they should have already been like equivalent to each other in the original type, right?
Yeah, I'm not quite sure. I'm sorry. Yeah.
Well, so I'm saying like the reason that this makes sense is because if you have a FG horn filled with H and one filled with H prime, and then you say, well, if the restriction is an equivalent,
right,
then the images of those two candidate composites under the restriction are the same object, which is equivalent to itself. So like if this is a homotopy equivalence, then like there should be a corresponding homotopy between the two unfilled horns, right?
That's right. So that's right.
So that's why it makes sense. It's not that there has to be a like a strictly unique composite, but it will be unique of the homotopy precisely when this happens.
So in this lingo, what you were saying, so since this is an equivalence, I mean by assumption it's also an embedding, and embedding gives you this that you can deduce, I mean, from the equivalence here already a path there. So okay, so this is not exactly the notion of infinity one category yet, but almost. So we're missing one sort of like technical ingredient. So first of all, an infinity one category is some object which should have composition, but also I mentioned that, well, I mean, we've seen that we have a notion of paths in every type, but we could also have a notion of isomorphism in every type, which could be something derived from our Hom types here. So we could also say, well, an isomorphism is, first of all, a morphism, which is, well, it should be invertible. So for some reason, that's not quite enough. I mean, we have to say what invertible really means. So in our case, invertible will mean that not only do we have, okay, the type that we want to look here at is the type of sort of bi-invertible maps where a priori we take two different inverses here, so a left and a right one. So conceptually it's not extremely important, but here it's the thing that we want to do. And the evidence of being inverses, that's again captured up to homotopy. But it will turn out to be that this is actually a good definition. So given an F, it's actually a proposition and not a whole space of data of being an isomorphism. That's essentially why we want this definition here. And the condition that we impose here is the condition that the following map is an equivalence. Namely, there's a canonical comparison map that we could call identity to iso, which witnesses that every path or every identification is also an isomorphism. And, well, the sort of condition is that these two notions of identifications, namely paths and isos, are equivalent. And the way to phrase this is saying this canonical comparison map is supposed to be an equivalence. So this is also called rest completeness in certain, particularly in certain homotopy theory. I mean, in certain higher categorical contexts that are just considering the semantics. This is like a sort of thing that occurs, and it reflects here in this way. And so, okay, let me wrap up with just saying what has been achieved in this theory. So, Riehl Shulman have introduced this theory. They've given like a basic account of synthetic infinity one category theory there. Saying what a functor is, natural transformation is, and so on. Plus, there's also a theory of discrete fibrations, homotopy coherent adjunctions, and there is a Yoneda lemma, which sort of can be understood as a directed version of the induction principle for these homotypes here. So I've briefly mentioned this induction principle of the identity types being generated by reflexivity, and there's an analogous thing for these discrete fibrations here, and it's kind of like a fibered Yoneda lemma. But can also be understood as this as a directed path induction principle. So remember, just for one categories, when you look at the Yoneda lemma, you also have the situation that the identity kind of generates the maps in question. And so there is some more follow-up work. I mean, there is some follow-up work generalizing parts of this due to Ulrich Buchholtz and myself. Where we look at not only discrete fibrations, but category valued or Cartesian fibrations, and plus some various generalizations. Then there is some work by Bardomiano Martinez on synthetic limits and co-limits in this setting. And there even, if for the people who are curious in playing around with this a little bit, there exists a prototype proof assistant implementation due to Nikolai Kudasov, which is called RESC, RZK, and you can find it on GitHub in this repository here. And there is sort of a parallel story which takes place completely in a cubical or bicubical setting, actually, due to Weaver and Licata. Which also has some ACTA implementation available. So it uses bicubical stuff rather than simplicial stuff, but it's also very much influenced by Riehl Shulman. And I thank you for your attention.
So I've been told by type theorists that there are all of these problems in homotopy type theory with defining simplicial or even semi-simplicial types. Is the idea here that we're kind of just moving all of that external to the theory with these judgments that we're adding?
It's kind of like that. So you do internal, so it's not, well, it's kind of extending. I mean, okay, so the problem that Brandon was pointing out is that if we just took homotopy type theory and we wanted to define something like really a coherently, sort of something like a homotopy coherent presheaf inside of it, and that's a big unsolved problem. Namely because no one succeeded in getting in sort of taming these increasingly appearing higher and higher coherences that you would have to deal with if you try to write down such a definition. And yes, here this problem is it's not solved, but it's circumvented by, well, yes, importing some more strictness, yeah, that's you could say, well, okay, it's importing something from the external world, or it's like some sort of partial strictification of the syntax, but it's definitely, I mean, it's something like this. So it definitely does not solve this problem of defining even semi-simplicial types internally in hot. Yeah. Yes, Nelson.
So I don't know if like the concept simplicity can be like, I mean, obviously you can do all of them in one category theory, but like they sometimes have more like natural interpretations in like two category theory. So can you do even a two category theory?
Not with this. I mean, not in the way that you want. I mean, you could interpret this in some, I mean, you sort of could take something which already is like internal categories, but I mean, that's not what you want. A colleague of mine, Lynn Moser, and I are thinking about some way that some external result about Siegel spaces that would allow us to do something like this. So yeah.
I'll go first just because it relates to Nelson's. It seems like the way this is set up, you just sort of take homotopy type theory, which describes spaces, and then kind of impose on top of that these Siegel conditions in the style of like complete Siegel spaces. It doesn't seem to me like there's anything stopping you from doing the exact same thing for like theta n spaces. So theta 2 spaces would give you infinity 2 categories, like what Nelson said, just replacing delta and these lifting conditions with the ones in theta 2. Am I missing something that makes that like?
It's a great idea, and it's exactly at least the case for n equals 2, you know, to begin with. What we're thinking about at the moment. I mean the point is that you want to have a nice internal condition, and to me it's not completely clear, but we're thinking about it. Yeah.
What happens if you just take the definition of a category from normal type theory and just import it into this?
Yeah.
You get double categories?
Okay, so for the simplicial hot case, I'm not sure. I don't know, but for hot, for instance, just for standard hot, that's something that people have considered. So it's like an analytic definition of a category inside. Exactly. But I don't think internally Yeah, sorry, I don't think externally it's the right thing. So I don't know exactly what you get, but it's I think it's less coherent than what you want, and it's certainly not on the nose quasi categories. Yeah. And
why do we want quasi categories?
well,
I don't want quasi categories. I want double infinity categories.
Double infinity categories. I don't know, but it would be good to think about that. Yeah.
Why don't we thank Jonathan again?
Yeah.